Good afternoon and welcome to the 21st annual exhibit of hydrogen and fuel cell technologies. We've been here for quite some time discussing innovations. This is an industry that is very much driven by research and development and innovation. We need the research facilities, those people who develop technologies, and it's always interesting to hear about the latest developments. We'll be talking to Professor Dr. Andreas Friedrich, who is head of the Department of Electrochemical Energy Technologies at DLR, Deutsche Luft, Raumfahrt, and we'll be talking about research and development for the next generation of fuel cells and electrolysis. Please welcome with me Professor Friedrich.
Hello, Brian.
Hello. Now, of course, such a large facility, Deutsche Luft, Raumfahrt, it's just enormous, but perhaps you could tell us a little bit about the field you work in, your institution, and what you do there.
Yeah, so as you said, the German Aerospace Center is a very large institution, about 7,000 employees, and working on space, aeronautics, transportation and energy. And we are actually associated to the energy sector, and we are working on electrochemical technology. So, for example, electrolyzers, fuel cells, and also batteries, next generation batteries.
Okay.
Yeah.
And of course, sometimes fuel cells and batteries are very closely related and integrated, so it really is the full field. Okay. Let's start with, surprisingly, a very important topic this year, electrolysis. Why it's important, we can go into that issue, but simply, you have evolved the technology of electrolysis.
Yes. Yes, so this was actually the starting point of my department at DLR. So in the 70s and 80s of the last century, DLR realized during the oil crisis that we needed new concepts, and then they started to look at hydrogen at that time with different concepts than today. But one thing was very important already then, is to couple alkaline electrolysis with renewable energy, so with photovoltaics or wind energy. So then we had a really large project called High Solar, where we started with the development of alkaline electrolysis for intermittent operation, meaning coupling it to photovoltaics or wind energy with fluctuating inputs. And this is the starting point of the department, and since then we have been working on these technologies.
Now, you mentioned fluctuating here. Whenever we talk about renewable resources, we always have that issue of their in the long run, they're reliable, but in the short run, they're off and on. It's a sunny day, it's a foggy day, or the wind's blowing, or it's not. Electrolysis is really an 18th century discovery, almost 19th century, I should say. But on the other hand, not all forms of electrolysis like to do fluctuation. Right. Does your electrolysis technology address this issue of fluctuate? I mean, if the wind turbines turn on and you lose the first 3 or 4 minutes and the wind's only blowing for 5, right, that's 80% of your energy wind. So is that something you address?
Yes, we address this in with several aspects. One is the cell technology itself. So for alkaline electrolysis, we have developed an electrode coating where we increase the surface area dramatically by having a specific plasma spray coating on a flat electrode surface, and thereby we increase efficiency, and we also increase the operation range of the electrolyzers, because you have to take into consideration that gases cross over the different compartments. And if you have better electrodes, this will reduce the crossover of these gases, so that you can also operate at part load with very high gas purity, so that you can use the whole range of the electrolyzers, not only one range at high current densities.
Okay, and there are you know, high temperature electrolysis technologies, low temperature. The high temperature may be great with efficiency, but the startup time and so on, it gets very complicated. Is this a low temperature or a high temperature electrolysis?
So the electrolysis I was talking about is a low temperature one in the range of 60 to 80 degrees C. And there you have two different technologies, which both of them are really interesting. That's the alkaline, which is very mature, but has some restrictions in which I talked about, and the PEM electrolysis, which has a membrane, and therefore the crossover of gases is reduced, and it has a very high power density. So we are working on both of them. One thing that we developed for the polymer electrolysis recently is corrosion-resistive coatings for the bipolar plates, which are normally fabricated from titanium metal, which, however, is expensive. And if you use a titanium coating, which we also apply by plasma spraying, then you can use stainless steel, or you could also use even other materials which have lower cost and therefore reduce the capex of the stack.
So a substantial reduction in cost for the with the titanium application. That's the electrolysis side, of course. For decades, I've been here since 1995. For decades, I've seen work in the field of fuel cell applications. In Deutsche Luft und Raumfahrt. You've got one spectacular display, which is right over here. Could you tell us a bit about what flies in your department?
Yes, so as a German Aerospace Center, we are of course very interested also in the aviation application. We are working together with Airbus on a so-called APU application, where it's not the airplane, the main propulsion of the airplane, but it's a system for onboard power supply, but we have a parallel development to also introduce fuel cells for propulsion of aircraft, of smaller aircrafts. We started several years ago with a motor glider for the pilot, essentially, which was equipped with a fuel cell and hydrogen technology, and now we are showing the project to develop a 4-passenger aircraft just with fuel cells and the batteries, or a hybridized system.
I recently learned how significant these auxiliary power units are. If you design a great jet, but it was designed earlier when people didn't want to power up their phones and watch movies constantly and have hot coffee served to them. That is, the turbines produce less electrical energy than people expect today. And we're constantly retooling transportation jets. And what is missing really is a redundant auxiliary power source that allows you to reconfigure a plane without having to replace the turbines. So this is a huge cost factor in the transportation industry.
Right, it's a huge cost factor, and it's really necessary from the regulations in the aviation, because every aircraft needs to be totally independent. So should not be dependent on the ground power supply, and you need an auxiliary power unit to start up the main engines. Otherwise, it would not be possible to start up the main engines everywhere. So only in airports where you have power supplies.
Okay. And similar units you're developing also for auxiliary power in the mobile sector, right?
Right, yeah, in a much smaller range. So in the power range of several kilowatts, we are interested in providing an auxiliary power unit for trucks. And there we want to use high temperature solid oxide technology, which fuel cell technology, which operates at about 800 degrees, because we are very flexible then in the fuel that we can use, and trucks will not shift in the near future to hydrogen because of the range they need, but they will stay with liquid fuels. And say a diesel fuel can be used very effectively in a high temperature fuel cell, but can provide auxiliary power unit power in a truck, which is necessary, for example, in the United States, where trucks drive for long distances, and then more or less the driver lives in his truck and needs power even for air conditioning and for sleeping, television and so on at night.
What I find so elegant about solid oxide fuel cells in that application is the flexibility of fuels. That is, PEM cells are really fussy. They want pure hydrogen.
Pure hydrogen.
Solid oxide fuel cells allow you to use the source of diesel. But potentially it's a transitionary. If we go to methane, it can also deal with that. It's very flexible, isn't it?
Yes, it's very flexible. It can even operate easier on methane or natural gas. So that's a possibility to shift with the solid oxide fuel cell, which is not present for the low temperature fuel cells.
And of course, it's a lot better than leaving the engine running. But what I find really interesting about it is if you've ever stood next to a truck with a conventional combustion source of energy, they have small motors on the sides, they leave these things, they're noisy.
Right, yeah, they're noisy. And we think that in future they will also, because they also emit quite a lot of emissions, they will be restricted. So we think that the future is on the fuel cell side here.
That's one of the best things about the fuel cells. They're so quiet. You do diagnostics as well.
Right.
We need doctors who look at actually what's happening within the cell and see what's happening. So some of your diagnostics capabilities are very specific for development. Could you...
Yes, so we have developed a segmented bipolar plate technology, meaning that we introduce a printed circuit board with segments into a fuel cell, and then you can detect the current density locally, in each segment, and so you get the distribution of current density over this area. And this is important because you have to realize that fuel cells manage media, manage gases, and therefore the conversion is never totally homogeneous. So you have heterogeneous distribution of current densities, but you need to avoid too much of this heterogeneity because it leads to lifetime issues. So with a segmented board installed into that, you can actually investigate the behavior and optimize your stack design and also optimize your cell composition in order to avoid degradation of the cells. And this we can do actually for low and high temperature fuel cells. For high temperature fuel cells it's a little bit more complicated, and for low temperature fuel cells actually our technology is commercially available.
It's always a pressure to have a professor on the stage because there's a philosophical perspective that you can require from these people. The industry is less philosophical sometimes, but in this philosophical perspective, there's a running debate and discussion about electrolysis. You've been involved in the field for a long time. We have such a potentially excessive quantity of electrical energy being generated from renewables in the north. Turbines is just one issue. Every time you turn a turbine off, people talk about efficiencies. A turbine that has been turned off is 100% inefficient. Right. It's just a waste of money. Turning off turbines is detrimental to the industry that is developing renewable energy. One of the solutions would be, of course, to use that electrical energy with electrolysis and create hydrogen. Next question. What are we going to do with all that hydrogen? Potentially, we are going to be overrun by quantities. It's a storage capacity. It may be. What do we do with it? Do we put it in the ground? Do we add it to the existing gas grid? How much can we add? Or we could do what's called methanization to turn it into something like natural gas. Do you have any policy preference or philosophical perspective on that?
Yeah, so I think that actually where we need most CO2 reductions right away is in the transportation sector. The transportation sector is emitting a lot of CO2 and it's not really improving very much in recent years. So I would say that the hydrogen produced would be best spent for the transportation sector, so used in fuel cell cars, where it also provides the highest benefit, economical benefit. If you use the natural gas grid, You of course have the problem that you're competing with the cost of natural gas, which is very low. It's about 3 cents per kilowatt hour, and therefore it's difficult to make a business case. But I think that you may be able to use this distribution system also for distributing hydrogen for use in cars, actually, for using then this distribution system that we have for the hydrogen fuel cell cars, if you can separate hydrogen and natural gas before the filling station.
Mm-hmm. Okay, that's an interesting take, and also allows us to move towards creating a hydrogen highway. If we had a separate grid for hydrogen, it is far too valuable a resource, perhaps, to simply dump into the existing. Well, this is when we get to philosophy, we could talk for hours, of course. I can only recommend that you visit Professor Friedrich at his stand, which is DLR. It's right there, D66, and raise your questions there. It's always a pleasure to talk to you, Professor Friedrich. Thank you so much for coming, and I hope to see you next year.
Yeah, thank you. Let me close with just telling you that DLR at the main booth over there has a reception this evening at 4 p.m. So you're all invited to come to our booth there.
Okay, 4 p.m. Be there or be square. Thank you very much.
Thank you.
And thank you. Up next, we'll be talking to Tom Stevenson, who is from Pararito Power, and they'll be talking about the true value proposition of low platinum catalysts. Welcome.